Hello. Here I will talk about one specific example of an algebraic number and the result of attaching it to the field of rational numbers and the symmetry group of this field. So this example will be the field of a number which is square root 2 plus square root 3. So this field and its automorphism group. Let's call this number for short alpha. And immediately we know that it is algebraic. Because, say, it is a sum of algebraic numbers. It is very straightforward to see the square root 2 and square root of 3 are algebraic, so their sum is algebraic by the general statement. But let's be more explicit and let's find the minimal polynomial for which alpha is a root. Well, let's start with just a polynomial for which alpha is a root, and the process is sort of inductive. We compute powers and we see linear dependencies, and the first one we see will have to be minimal, but yeah, let's just see some linear dependence. So we'll compute powers. Let's compute the square. The square by the binomial formula will be the square of the square root of 2, which is 2, plus the product of these two twice, so that will be square root 6 twice, plus the square of the square root 3, which will be 3. So together 2 and 3 will give us 5. Now we'll have 2 square roots of 6. And let me do some little trickery, so let me just take 5 on the other side. Alpha minus 5 will be equal to the twice the square root 6. So if I take alpha squared minus 5 and squared, I will have the square of this, which will be 4 times 6 will be 24. And if I expand the square, I'll have alpha to the 4th minus 10 alpha squared plus the square of 5, which is 25, all equal 24. So now putting 24 on the left, I will have a polynomial, sorry, it is a 4th power, a polynomial relation on my alpha, which manifests the algebraicity of alpha. So I will be done with this minimal polynomial finding if I will show that this is an irreducible polynomial. And this is an irreducible polynomial. Well, when I say irreducible, I have to specify over which field, and the basis field of rational numbers is what I have in mind. So how can I see that this is an irreducible polynomial? Well, if it is reducible, it has to factorize into a product of at least 2. And since it has degree 4, factorizations could be in degree 1 and degree 3, and that means that I will have a root. But I can see that there are no roots of this polynomial in rational numbers, because roots in rational numbers will have to be integer roots by Gauss's lemma, and will have to be divisors of 1, so will have to be plus or minus 1. If I substitute in this polynomial, call it f, if I substitute either plus or minus 1, I will not get 0, so that is the way of dismissing rational roots. So all I can have in the factorization department is a product of 2, quadratic. And how can they be looking like? So again, looking at the leading coefficient, it can be made 1 for both, and then looking at the free coefficient, they have to multiply into 1, they have to be integer by Gauss's lemma again. So I could have 1 and 1 with plus, and then some coefficient for t in each of these quadratics. So if I call this coefficient a in the first, then it's easy to see that in the second I have to have negative a, because linear terms have to cancel out. Right? If I start opening, so if I have some numbers or some number of copies of t in here, then multiplying with 1, I will have to match it with the product of that number of copies of t multiplied with 1 again, so the number of copies have to be inverses of each other. And if I now compute completely the product expanded completely, I'll have t to the 4, and then I'll have no t cubed, again it will cancel out, and then I'll have t squared. So what is the coefficient for t squared? T squared is coming from t squared with 1, t squared with 1, so that gives me 2t squared, and then I have negative a squared. And then of course I have the free coefficient 1. So that is to happen if I have this factorization. And then matching it with what I have, negative 10, I can see that a squared has to be equal to 12. And that is not possible to solve in rational numbers, so I don't have this type of factorization. Alternatively, I could have coefficient negative 1, and that's all I can have. Among integers multiplying into 1. And again, if I call this at, then this has to be negative at, due to the same reason linear terms have to cancel in the product. So expanding it again, oops, t to the 4. I have maybe putting minus overall in front. I have 2 plus a squared, t squared plus 1. So that case will be giving me a squared being equal to 8. And again, it is not possible to solve in rational numbers. So that's why my polynomial is irreducible. I cannot factor it at all. Since it is irreducible, I know that my field, the result of attaching my alpha, is a degree 4 extension. It is as a ring isomorphic to the quotient ring by this polynomial t to the 4th minus 10 t squared plus 1. And as a vector space, it is spanned by powers of alpha, starting from the 0 power down to all the way to the 3rd power. So that is a nice concrete description of my field. And computing the group of its symmetries, I will be better off choosing a different basis. So that's what I'll do now. I will do some little trickery. So first is to look at this equation. Well, it's just an expression of square root 6 effectively. So square root 6 will be alpha squared minus 5 halved. So it's one of my numbers. It's a combination of alphas, specifically this combination, which gives me square root 6. So I'm going to write square root 2 and square root 3 as well as combinations of alphas. And yeah, you could see how it is going to come out. So if I take alpha and I multiply by the square root of 6, which is alpha squared minus 5 halved, what I will have is, okay, this is square root 2 plus square root 3, what alpha is, and then this guy is the square root of 6. I'll have this together will give me twice the square root of 3, and this 2 in the product will give me 3 times the square root of 2. So now if I have this and if I have my alpha, I can manufacture separately the square root of 2 and the square root of 3. So the square root of 2 I can get by taking this and subtracting 2 copies of alpha. So that will be alpha times alpha squared minus 5 over 2 minus 2 copies of alpha. Right? Because if I take this twice and subtract from here, I will have just the square root of 2 surviving. And the negative square root of 3 I can get by taking again alpha times alpha squared minus 5 over 2 and subtracting 3 copies of alpha. I can then negate both sides and have just an expression of the square root of 3. And you could see that this polynomial answers for the square root of 2 and square root of 3 are all linearly independent. So instead of this basis, I could use a different basis for my field. But let me first record the fact that this is also the same as a field of attaching 2 numbers in a sequence or altogether, separately square root 2 and separately square root 3. They both are in this field, and having them separately, I can of course manufacture their sum. So these are the same fields. And moreover, I have a different basis, a more convenient basis for my field now, this is the basis. So the rest will be computing the group of symmetries. To just try the placeholder for the answer. I love it rational, so just the whole group of symmetries. What I could do, of course, I could just start with the minimal polynomial. Here's a minimal polynomial, find all its roots, and the roots will be labeling my symmetries, and then I could look at the group structure of the corresponding maps, defined by the condition that T here goes to the root. I have a better way using this presentation. I have a better way of doing it. So having this alternative description of our field, we could see two subfields inside it, the result of attaching just the square root of 2 and just the square root of 3. So I'll draw this partial lattice, just part of the lattice of subfields of this larger field, and then I put plus here because it's the same field, and then the indices have to be all 2 because we know that these indices are 2, and then these have to be 2 because the overall index has to be 4. So that is the separate information which is going to help me computing my symmetry group. So now I could look at, say, symmetries which will not move this subfield around. So I will look at the subgroup in here of the symmetries which will fix the square root of 2. So all my symmetries will be not moving the square root of 2. And what can they do instead? Just after this, they can only move around the square root of 3. So the square root of 3 is what determines the value on the square root of 3. And of course we can move the square root of 3 into plus or minus. So we'll have two such symmetries. And looking at the other end, we can look at symmetries which are fixing the square root of 3. So that would be, I'll call them differently, I'll call them C's. They will be treating the square root of 3 as a scalar, and then what is left for them to move around is the square root of 2, and again it can be moved into plus or minus this C. So I have two copies of them as well. And they both symmetries of the larger field, they're just fixing some subfields. So I have already 4 different, let me combine them, I'll just call it phi, but I'll have 2 subscripts for it, a pair of signs, and it will be just compositions of those. So I will write down, let me write here the complete description of elements, as I said, a plus b square root 2 plus c square root 3 plus d square root 6. A, b, c, d are rational numbers. So in this way of writing, I'll just take an arbitrary number from my field and write what this. So maybe I'll have to call them signs, some Greek letters like mu and nu. So mu and nu are going to be plus or minus, and then A is just fixed altogether. So mu will be the sign of this, what I do with the square root of 2. So that will be appearing in front of the square root of 2, and also in front of the square root of 6, because the square root of 6 is the product of the square root of 2 and the square root of 3. And then nu will be the sign of the square root of 3, the result of applying to it. And also I have the square root of 3 inside the square root of 6, so nu has to come up in here as well. And that is a complete description of all my symmetries. So my group is of 4 elements, these phis with labels mu and nu separately are in the group of plus or minus 1. as an abstract group, this is the product of two cyclic groups of order 2. So what we see here is that our degree 4 extension has maximal amount of symmetries, 4 symmetries for degree 4. That means that this is a Galois extension. Of the rationals. And now we can go back and we could just find all other roots of our, say, irreducible polynomial here, which would exhibit the fact that this is a splitting field for this polynomial. So the polynomial has all its roots inside the field that is equivalent to having the maximum amount of symmetries. So I could write the factorization for this polynomial t to the 4 minus 10 t squared plus 1 in this field, and that will be t minus, say, the original number square root 2 square root 3. Then we could apply all our non-trivial symmetries one by one and see what the Galois conjugates of this number are. So there will be, say, changing the sign of square root 2 separately, so we'll have plus square root 2 minus square root 3. Then we have t, say, minus square root 2 plus square root 3, and then changing the signs for both the square root 2 plus square root 3 and then the bracket. So that is a complete factorization into linear terms of our irreducible polynomial over the rationals. And that is a factorization in the field of this number square root 2 plus square root 3. More examples are to come. Stay tuned. Bye.